So what are the general properties of acids and bases? So let's separate them here. Acids on the left and bases on the right. So you already know that acids, they taste sour. Bases, on the other hand, they taste bitter. Acids will turn litmus paper red. Bases, acids and bases, they neutralize each other. So acids, let's just go with neutralizes the base, and then the base will neutralize the acid. Bases feel slippery and soapy. Let's see what else. Acids will react with metals. Via a single displacement reaction. So that releases a hydrogen gas. So these are the general properties that you need to know regarding acids and bases. So there are several different definitions of acids and bases. We talked about, let's see here, the Arrhenius definition. So the first one is Arrhenius definition, the second one is the Bronsted-Lowry definition, and the third one is actually Lewis definition. And we didn't really cover the third one because this is typically covered in advanced courses like organic chemistry. But let's define what Arrhenius acid is and base. So according to Arrhenius, an acid is anything that produces a hydrogen ion. So this produces a hydrogen ion. And a hydrogen ion is also known as a proton. Okay, so this is a proton. On the other hand, a base is any compound that produces a hydroxide ion. So this produces a hydroxide ion, OH with a negative charge on the oxygen. So this is called a hydroxide ion. So that's the Arrhenius definition of acid and base. And there's a lot of different ones. For example, for an acid, you can have HCl that gets ionized in water to form hydrogen ion and a chloride ion. So as you can see, it released a hydrogen ion. An ionic compound that is a base is NaOH. So in water, this will release hydroxide ions and sodium ions. The Bronsted-Lowry definition, let's take a look. So for an acid, it would be a proton donor. It donates a proton. So the Arrhenius definition of an acid overlaps with the Bronsted-Lowry definition. The base would be the proton acceptor. Proton acceptor. So anything that any compound that has the ability to accept a proton is considered a Bronsted-Lowry base. And a lot of these compounds contain at least a lone pair of electrons. So if you see any compounds, like for example NH3, when you draw the Lewis structure, that nitrogen atom has a lone pair of electrons, and so it can act as a base. So this is NH3 or ammonia. Water can also act as a base because it contains lone pairs of electrons. Likewise, both of these molecules can also act as an acid. And the reason why is because they contain hydrogens. These hydrogens are protons. They can be donated. And so that means ammonia and water can act as an acid and also as a base. And the term here is amphiprotic. So they can accept a proton, they can also donate a proton. The Lewis acid definition, Lewis acid base definition, you don't really need to know, but in an acid, a Lewis acid is anything that can accept an electron pair. So this is an electron pair acceptor. And a base would be an electron pair donor. Okay, so the Bronsted-Lowry acid base definition is based off of proton. Is it a donor or an acceptor? But in the Lewis acid base, it's in terms of an electron pair. Is it an electron pair acceptor or an electron pair donor? All right, the next concept here is ionization of an acid in water. So how do we show the ionization of acid in water? So there's two different ways. Let's say, for example, HCl, hydrochloric acid. When you put this in water, HCl gets ionized into a hydrogen ion and a chloride ion. So that's the first way. The second way is by actually including water in the chemical reaction equation. So you have HCl plus water, H2O. And what you get is a hydronium ion, H3O plus, and a chloride ion. So this H3O plus is called a hydronium ion. And here's another example. We can have, let's say, nitric acid, HNO3. When this gets ionized in water, it releases a hydrogen ion and the nitrate ion, NO3 with a negative charge. Okay, so that's one way. Another way is including water in the equation, NO3 plus H2O. And you get H3O plus and the nitrate ion. All right, and we can show you another example here. Let's say sulfuric acid, H2SO4. H2SO4 will generate a hydrogen ion and HSO4 with a negative charge. Okay. And then the other way is to include water again, H2O. And this will turn into H3O plus and HSO4 minus. you can see here that sulfuric acid contains 2 ionizable protons. So that means that this HSO4 with a negative charge can undergo second ionization. Okay, so HSO4 minus will turn into H plus plus SO4 with a -2 charge this time. Showing this in water would look something like this. H3O plus the sulfate ion. All right, so 4 different examples here. And we could also do the same thing for the dissociation of bases in water, not just acids. So again, bases, they contain a hydroxide ion, right? So if you have lithium hydroxide, sodium hydroxide, let's say magnesium hydroxide, and let's say um, calcium hydroxide. How do we show the dissociation of bases in water? So we can go ahead and put AQ here for aqueous to indicate that they are in water. They are dissolved in water. So in water, they would dissociate into ions, Li plus and hydroxide. All right, and you always have to indicate that it is in water, so you're gonna put aqueous here. We can do the same thing for sodium hydroxide, Na plus in aqueous, plus hydroxide in aqueous. Okay, for magnesium hydroxide, it's gonna be slightly different. We have Mg with a +2, again aqueous, plus this time we have 2 units of the hydroxide ion. So you have 2 moles of the hydroxide ion here, again in aqueous solution. Same thing for the calcium hydroxide. We have Ca2 plus in aqueous plus 2 moles of the hydroxide ion. All right, and that's how you show the dissociation of bases in water. Another concept that you need to know for the test from chapter 12 is the difference between monoprotic and polyprotic acids. So let's take a look at a few examples here. All right, so mono means 1, and poly means many, more than 1, right? And so protic is the term for proton, the number of ionizable hydrogen, right? So this is a hydrogen. How many hydrogens are there in the chemical formula? So monoprotic then means an acid containing 1 hydrogen. Okay, and polyprotic is an acid with more than 1 hydrogen. Now let's take a look at a few examples. Let's say for monoprotic, we have binary acids like HCl, it's hydrochloric, HBr, HI hydrofluoric. So these are all good examples of a monoprotic acid. I mean, you can also have a hydrogen sulfate acid, HSO4, with one ionizable proton. You can have HPO4 2 minus. It has one ionizable proton. So these are all examples of monoprotic acids. Polyprotic contains more than one hydrogen, and so sulfuric acid is a good example containing two hydrogens. You can have H3PO4 phosphoric acid with three ionizable protons. All right. Um, so now let's look at a few examples of Bronsted-Lowry acid-base type of reactions. If you remember a Bronsted-Lowry acid, so let me just write that down here. Oops, hold on a second. So again, a Bronsted-Lowry acid is a proton donor. An acid, a Bronsted-Lowry acid donates a proton. A Bronsted-Lowry base is a proton acceptor. So here's a few examples of Bronsted-Lowry acid-base reactions. There's a total of 4 here. And let's try to determine which one is the Bronsted-Lowry acid and which one is the base. So when you look at the first one here, the first equation or first chemical reaction is between ammonia and water. And what happens to ammonia after the reaction with water? Well, it turns into NH4 plus, right? The NH3 turned into NH4 plus. So it tells you that the ammonia is the one that accepted a hydrogen, right? So accepted a hydrogen ion. It accepted a proton. So in that case, according to the Bronsted-Lowry theory, NH3 is the base. So this is the base, and water is the one that's acting acting as an acid. Because water, H2O, turned into OH minus, it donated a proton. It donated a hydrogen. So that counts as an acid. What about in the second example? We have HSO4 minus reacting with water. And when you look at water right here, it turned into H3O plus. It accepted a hydrogen. And so in that case, water is the one that's um, acting as a base. So water is the base, and therefore the other one must be the acid. You can see that HSO4 with a negative charge turned into SO4 with a negative 2 charge. So you can see that it donated a hydrogen. Third one here is HNO2 with phosphate. The phosphate turned into HPO4. So it accepted a hydrogen, and therefore it's the one that's acting as a base. And HNO2 then is the acid. And the fourth one here, we have HClO3 turning into ClO3 minus. So it lost a hydrogen ion. So it donated a hydrogen, therefore it's an acid. And that makes this compound right here the base. And that's all you need to know regarding Bronsted-Lowry acid base. The next concept here, this is probably the last concept regarding chapter 12, is the pH scale. So pH scale is a range of numerical value between 0 and 14, and then the middle one is 7.0. So the pH scale basically tells you whether a sample or a solution is acidic, basic, or neutral. So if it's between 0 and 7, then you know that the sample is acidic. If it's between 7 and 14, you know it's going to be basic. And if the solution, if the pH is between 0 and 2, then you know it's going to be strongly acidic, that it's going to be a strong acid. But if it falls between 2 and 7, that's going to be weakly acidic. And then if it falls at exactly 7.0, it's going to be a neutral solution, a neutral sample. So it's neither acidic nor basic. Water, for example, is neutral. If if it falls between 7 and 12, pH value of 7 and 12, then you know it's weakly basic. Otherwise, it's going to be strongly basic. And there's a lot of different ways you can determine the acidity or the basicity of solutions. You can use pH strips or pH papers as shown here. It'll tell you what what the pH, what the actual pH value is based on the color change. So you're going to dip the pH strip into the liquid sample, and then based on its color, if it's, let's say, yellow or um, somewhere around yellow, then you know that it's a neutral sample. But if it turns slightly red, then you know it's going to be an acidic sample. If it's somewhere around bluish, greenish region, then you know it's going to be basic. You can use other, more accurate pH strips. Like for example, this one ranges between 4.5 and 7.5. So it's more accurate by zero point 0.5, right? So if you want to just test between 4.5 to 7.5 pH, you can use this specific pH strip. But if you want a really accurate determination of the pH, you can use a pH meter, which of course is a little bit more expensive. So it uses a pH probe here. So you're going to dip this probe into the sample, the liquid sample, and then it'll spit out a number. And that number, based on the number, it can be acidic or basic, right? And so when you operate something like this, you have to calibrate um, you have to calibrate the machine using what they call buffer solutions. So if you want to measure the sample, which potentially has a pH between, let's say, 4 and 7, then you would have to calibrate the machine within that pH range using buffer solutions. All right, and the last thing that we want to talk about is chapter 13, which is all about reaction rates and the factors that affect reaction rates. So what is reaction rate? It's basically the speed at which chemical reactions take place. It tells you how fast a chemical reaction is. Some chemical reactions happen very slowly. Some chemical reactions happen very, very quickly. And there are several factors that affect reaction rates. And there's three of them that we talked about in this chapter. The first one is uh, temperature. So factors that affect reaction rate, we have temperature. The other one is concentration. And the third one is activation energy. All right, so temperature affects the speed at which the molecules are moving around. Remember that a chemical reaction happens when the molecules collide in solution. Okay, so the faster the molecules are moving, the higher the likelihood that they will collide with each other and cause a chemical reaction. So increasing the temperature would increase the reaction rate. Same thing with concentration. The higher the concentration, the more molecules you have in the sample. And so higher number of molecules increases the likelihood that the molecules will collide with each other and cause a chemical reaction. And so increasing concentration, increasing increases the reaction rate. So let me write that down. So increase in temperature increases the reaction rate. Okay. Increasing the concentration would also increase the reaction rate. So they are uh, directly related. Activation energy is the inverse. Activation energy, by definition, is the energy required to activate the chemical reaction, itself. So the higher the activation energy, the more energy required, the more energy is required to jumpstart that chemical reaction. So higher activation energy decreases the reaction rate. So those are the three factors that affect reaction rates. All right, so the next one here is reaction energy diagrams, activation energy, and the net energy change. So in a lot of chemical reactions, um, we can explain the mechanism of chemical reaction by knowing the reaction energy diagram. So let's take a look. So what does a reaction diagram, energy diagram looks like? So let's say we have the x-axis here, we have the y-axis, energy is on the y-axis, and then time would be on the x-axis. So this is the progress of the reaction. All right, so time moves from left to right, energy increases from bottom to top. So let's say that we have reactants on the left-hand side, your starting materials before the chemicals react, and then the final would be the products. So we have products right over here. And initially, the reactants are at a low energy, and then once they start colliding with each other, there's an increase in energy. So it goes up. And then bonds are going to be forming, bonds are going to be breaking. And so it reaches the highest point, highest energy possible. And once the reaction calms down, then you have mostly uh, formed bonds and mostly broken bonds. Okay, so you have a decrease in energy here until you reach the most stable form of the products. So the difference in the energy between reactants and this highest peak right here is the activation energy. Okay, and the highest peak right here is what they call the transition state. And again, the transition state is basically the state of the chemical reaction in which you have a hybrid uh, structure containing partially broken bonds and partially formed bonds. And then the delta H here is the net energy change between the products and reactants. So it's essentially the difference in the energy between the products and the reactants. So this is what they call delta H, the net energy change. All right, so this is a specific example here in which the energy of the products is greater than the energy of the reactants. We have uh, an, an endothermic reaction. Okay, so this is an endothermic reaction. We have delta H being positive here, greater than 0. So this is endothermic. If it's the other way around, if the energy of the reactants is greater than the energy of the products, then you know that the delta H or the net energy change is going to be negative, less than 0. And if that's the case, then you know that it's going to be an exothermic reaction. All right. And second to the last concept here that I want to talk about, catalysts and how that affects the activation energy and the energy diagram itself. So let's take a look. So by definition, a catalyst speeds up a chemical reaction. So this a speeds up the rate, the reaction rate, speeds up the reaction rate. Okay, and it does that by reducing the activation energy. All right, so what would the energy diagram look like between a catalyzed reaction and uncatalyzed reaction? Let's take a look. So again, here's our energy diagram. Time on the x-axis, energy on the y-axis. So for a catalyzed reaction, let's say we have um, reactants on the left, we have reactants here, and then we have products here. For an uncatalyzed reaction, it would look something like this. So this is uncatalyzed. And you can see that the activation energy is quite high. For a catalyzed reaction, it would reduce that activation energy. So it would look something like this. So this would be a catalyzed reaction. All right, so I made this a little bit lower energy, but this is supposed to be, let me just redo that again. So it doesn't affect the net energy change. There we go. So a catalyst, so I'm going to add this right here, does not affect the net energy change. So a question on the test might be, which one of the following affects delta H? Right? A catalyst does not affect delta H. So that's all you need to know regarding this slide here. And the last one, I apologize again for taking a long time for this review. There's just a lot of materials. All right, and the last one here is how do we calculate activation energy and the net energy change? So I'll just give you an example here. I'll give you a chart, again, an energy diagram. And let's say we have the reactants here, and then the products right up here.
We can't see your drawing.
All right, thank you. All right, so here's the energy on the y-axis and time reaction progress on the x-axis. And let's say that the highest peak right here is 100 kilojoules of energy. And the energy of the products is, let's say, 60. And the energy of the reactants, let's say, 30. So how do we calculate the activation energy? So again, the activation energy is the energy of the difference in the energy between the reactants and the highest peak. Okay, so that would be 100 minus 30. So activation energy equals 100 minus 30, and that's 70 kilojoules. Assuming that this is in kilojoules per mole. Okay, so that would be kilojoules per mole. All right, and the delta H can be calculated, again, by taking the difference between products and the reactants. So that would be right here. So 60 minus 30, right? So it's the energy of the products minus energy of the reactants. So delta H equals energy of the products minus energy of the reactants. That would be 60 minus 30, and we get a positive number, positive 30 kilojoules per mole. And because delta H is a positive number, you know that this is going to be an endothermic process. All right, so that's all I have for today. If you guys have any questions, let me know. Otherwise, I'll see you all on Wednesday.